Right now, at this very moment, a bubble of destruction could be expanding through the universe at the speed of light. Inside this bubble, the fundamental constants of nature are different. Atoms cannot hold together. Matter as we know it cannot exist. The laws of physics themselves are rewritten, and we would never see it coming. This is not science fiction. This is not speculation. This is a prediction that emerges directly from the equations that describe our universe. The vacuum of space, the very fabric of reality itself, may be fundamentally unstable. We may be living in what physicists call a false vacuum that is waiting to decay. What if the emptiness of space is not as empty as we think? What if the void itself is in a temporary state, metastable, like water that is cooled below freezing but has not yet crystallized into ice? What if everything we know about reality exists in a precarious balance that could collapse at any moment? Today, we journey through the evidence that challenges everything we believe about the stability of existence. Prepare yourselves. We begin. In 1973, a young physicist named Sidney Coleman was working through equations that described the quantum nature of empty space when he made a discovery that would haunt him for the rest of his career. Coleman was investigating the nature of the vacuum, that seemingly empty void between particles. What he found was deeply unsettling. The vacuum, Coleman realized, was not a passive stage upon which physics plays out. It was an active participant. It had energy. It had structure. And most disturbingly, it might not be stable. To understand why this matters, we need to revisit what we mean by vacuum. In everyday language, a vacuum is simply empty space, devoid of matter. But in quantum physics, the vacuum is anything but empty. It seethes with activity. Virtual particles constantly pop into and out of existence. Quantum fields permeate every point in space. The vacuum has an energy density, a value that determines the fundamental properties of our universe. Here's the critical insight. There can be multiple possible vacuum states, each with different energy levels. Think of a ball resting in a valley on a mountainside. The ball is stable there, but if you could somehow transport it to a deeper valley on the other side of the mountain, it would release energy as it rolled downward to that lower state. It was stable in the first valley, but not in the lowest possible energy state. Our universe, Coleman's equations suggested, might be like that ball in the higher valley. We exist in a vacuum state that seems stable, but it might not be the true vacuum, the state of lowest possible energy. We might be in what physicists call a false vacuum. The implications of Coleman's work became clearer as other physicists began exploring the mathematics. In 1977, Coleman and Frank DeLucia published a paper that would become legendary in theoretical physics circles. The paper, titled Gravitational Effects on and of Vacuum Decay, described exactly how a false vacuum would decay. The process begins with a quantum fluctuation, a random event that occurs somewhere in space. In this fluctuation, a tiny bubble of true vacuum appears, perhaps no larger than a subatomic particle. In our ball on a hillside analogy, this is equivalent to the ball spontaneously tunneling through the mountain to reach the lower valley on the other side. Under most circumstances, such a bubble would immediately collapse and disappear. But Coleman and DeLucia showed that if the bubble reaches a critical size, it becomes stable, and then it begins to expand. The wall of the bubble, the boundary between false vacuum and true vacuum, races outward at nearly the speed of light. Everything the bubble touches is transformed. Inside the bubble, the vacuum energy is lower. This means the fundamental constants of nature, things like the mass of the electron or the strength of the electromagnetic force, have different values. Atoms bound together by one set of physical laws suddenly find themselves in a universe with different rules. They cannot survive the transition. The bubble expands forever, converting the false vacuum universe into true vacuum, leaving destruction in its wake. And here's the truly terrifying part. We would never see it coming. Because the bubble wall expands at nearly the speed of light, and light itself travels at the speed of light, there would be no warning. One moment you exist, the next moment the bubble wall has passed through you, and you have ceased to exist in any meaningful sense. For decades, vacuum decay remained an interesting theoretical possibility, something physicists discussed in graduate seminars, but not something that kept them awake at night. The mathematics was elegant, but there was no way to determine whether our universe actually existed in a false vacuum state. The question seemed unanswerable. Then came July 4th, 2012. At CERN's Large Hadron Collider, physicists announced the discovery of the Higgs boson, the particle responsible for giving other particles their mass. The discovery was celebrated worldwide. Peter Higgs wept at the announcement. It was the culmination of a 50-year search and confirmed one of the most important predictions in all of physics. But embedded in the properties of the Higgs boson was a disturbing revelation. The mass of the Higgs, measured at approximately 125 GeV, billion electron volts, fell into a very particular range. This mass, combined with the mass of the top quark, another fundamental particle, allowed physicists to calculate something they had never been able to calculate before: the stability of the vacuum. Within months of the Higgs discovery, papers began appearing with titles like Stability of the Electroweak Vacuum and Critical Look at the Metastability of the Standard Model Vacuum. The conclusion? Our universe appears to be metastable. We are living in a false vacuum. But the evidence forces us to confront an uncomfortable possibility. The very fabric of reality may be temporary. The Higgs mass problem. The Higgs boson mass of 125 GeV sits in what physicists call the metastability window. If the Higgs had been slightly lighter, say around 120 GeV, our vacuum would be absolutely stable. If it had been slightly heavier, perhaps 130 GeV, our vacuum would be completely unstable, already decaying. But at 125 GeV, we're balanced on a knife's edge. In 2012, a team led by Giuseppe Di Grassi at the University of Rome performed detailed calculations of vacuum stability using the newly measured Higgs mass. They computed what's called the effective potential of the Higgs field at different energy scales. At low energies, the energies we experience in everyday life, the potential has the right shape. The vacuum is stable. But as you calculate the effective potential at higher and higher energies, the potential develops a second minimum, a deeper valley. The transition occurs at an energy scale of approximately 10 to the 10th power GeV, or 10 billion GeV. This is far beyond anything we can create in particle accelerators. The Large Hadron Collider, the most powerful accelerator ever built, reaches energies of around 14,000 GeV, or 14 TeV. The energy scale where the vacuum becomes unstable is roughly 1 trillion times higher than what we can produce experimentally. This means the vacuum decay we're discussing would not be triggered by anything humans could do. The energies required are those that existed only in the first fraction of a second after the Big Bang. But those energies did exist once, and quantum mechanics tells us that even without reaching those energies, vacuum decay could occur through quantum tunneling, the same process that allows the bubble to form spontaneously. The top quark connection. The top quark, the heaviest of all fundamental particles, plays a crucial role in vacuum stability. Discovered at Fermilab in 1995, the top quark has a mass of approximately 173 GeV, making it heavier than an entire gold atom. This extraordinary mass means the top quark has the strongest coupling to the Higgs field of any known particle. In 2013, researchers at the University of Copenhagen, led by Jens Krogh, performed precision calculations showing how the top quark mass affects vacuum stability. They found that if the top quark were just 5% lighter, our vacuum would be absolutely stable. If it were 5% heavier, we would already be doomed, living on borrowed time as quantum fluctuations inevitably spawn a decay bubble somewhere in the observable universe. The fact that both the Higgs and top quark masses fall into this narrow metastability window seems either remarkably fortunate or deeply mysterious. Physicists calculated that if you randomly selected these masses from reasonable ranges, the probability of getting values that produce metastability rather than absolute instability is less than 1%. We appear to be either extremely lucky or there's something we don't understand about why these particles have the masses they do. Quantum field theory predictions. The standard model of particle physics, our best description of fundamental forces and particles, makes specific predictions about vacuum stability. In 2015, a comprehensive analysis by Alekin, Dujati, and Muk combined all available experimental data on particle masses and coupling strengths to produce the most accurate vacuum stability calculations to date. Their results painted a concerning picture. Using the best measurements available, they calculated that our vacuum is metastable with a confidence level of 98%. Only 2% of their analysis allowed for the possibility of absolute stability, and that possibility required the particle masses to be at the extreme edge of their experimental uncertainties. The calculations also revealed something unexpected. The lifetime of our false vacuum, if we exist in one, depends critically on the rate of quantum tunneling. Using quantum field theory, physicists can calculate approximately how long we should expect our vacuum to survive before a decay bubble forms somewhere in the observable universe. The answer is staggering: 10 to the power of 600 years. This is not 10 times 600. This is 1 followed by 600 zeros. For comparison, the current age of the universe is approximately 10 to the power of 10 years. The false vacuum, while unstable, is extraordinarily long-lived. The cosmological constant mystery. There's another piece of evidence that points toward vacuum metastability, and it comes from cosmology rather than particle physics. The cosmological constant, also called dark energy, describes the energy density of empty space itself. Observations of distant supernovae in the late 1990s revealed that the expansion of the universe is accelerating, driven by this mysterious dark energy. The measured value of the cosmological constant is tiny, approximately 10 to the negative 120th in natural units. This is one of the smallest non-zero numbers ever measured in physics. But here's the puzzle. Quantum field theory predicts the vacuum energy density should be enormous, perhaps 10 to the power of 120 times larger than what we observe. This discrepancy of 120 orders of magnitude is called the cosmological constant problem, and it's one of the deepest mysteries in physics. Steven Weinberg, Nobel laureate and one of the architects of the Standard Model, pointed out in a 1987 paper that the smallness of the cosmological constant might be evidence of metastability. If we exist in a false vacuum, the vacuum energy density reflects the energy of our current state, not the true vacuum. The tiny value we observe might be telling us that we're not at the bottom of the energy landscape. We're teetering on a ledge. But this represents just one piece of a much larger puzzle hidden in the mathematics of quantum fields and space-time itself. Gravitational effects on decay. Sidney Coleman's original analysis of vacuum decay assumed flat spacetime, the geometry of space described by special relativity. But our universe is not flat. General relativity tells us that mass and energy curve spacetime, and this curvature affects the vacuum decay process in unexpected ways. Coleman and De Lucia's 1977 paper incorporated gravitational effects into the decay calculation. What they found was remarkable. Gravity actually speeds up vacuum decay. The reason is subtle but profound. When a true vacuum bubble forms, the difference in vacuum energy between the inside and outside of the bubble acts like mass. This mass curves spacetime, and the curvature affects how the bubble expands. In 2015, physicists William East, John Croney, and Hitoshi Murayama and others at Berkeley performed detailed numerical simulations of vacuum decay, including gravitational effects. They discovered that once a bubble reaches a certain size, gravity takes over. The bubble doesn't just expand at a constant rate, it accelerates. The bubble wall can even exceed the speed of light relative to observers in the false vacuum outside, though it never exceeds the speed of light locally. This is possible because space itself is expanding. The simulations revealed another disturbing feature. The gravitational effects of a large decay bubble would be detectable as gravitational waves, ripples in spacetime. In principle, if a vacuum decay bubble formed anywhere in our cosmic horizon and grew large enough, we might detect the gravitational wave signature before the bubble wall reached us. Might. The warning time would be minimal, but it would exist. Experiments like LIGO and future space-based gravitational wave detectors could, in theory, provide humanity with a few seconds or minutes of notice before annihilation. Black holes and vacuum catalysis. In 1978, physicist Frank Wilczek, who would later win the Nobel Prize for his work on the strong nuclear force, investigated whether black holes could trigger vacuum decay. The energy density near the edge of a black hole's event horizon reaches extraordinary values. Wilczek wondered whether these extreme conditions could catalyze the formation of a true vacuum bubble. His calculations suggested yes. A black hole could potentially nucleate vacuum decay, acting as a seed crystal around which true vacuum forms. The probability is still extraordinarily small, but it's higher than the probability of vacuum decay occurring in empty space through pure quantum tunneling. This led to a disturbing realization. The universe is full of black holes. Every large galaxy contains a supermassive black hole at its center. The Milky Way's central black hole, Sagittarius A star, has a mass of 4 million times our Sun. The galaxy M87, made famous by the Event Horizon Telescope's first black hole image, contains a black hole with a mass of
cosmic rays and high-energy events. If vacuum decay can be triggered by high energies, what about cosmic rays? These are particles, mostly protons, that constantly bombard Earth from space. Some cosmic rays carry enormous energies, far exceeding anything the Large Hadron Collider can produce. In 1991, the Fly's Eye detector in Utah detected a cosmic ray proton with an energy of approximately 3 × 10⁻20 electron volts. This single proton carried as much kinetic energy as a baseball thrown at 60 miles per hour. The event was so extraordinary that physicists nicknamed it the "Oh my God" particle. Since then, hundreds of ultra-high energy cosmic rays have been detected. These particles carry energies that approach the energy scale where, according to calculations, the vacuum might become unstable. Why haven't they triggered vacuum decay? The question troubled physicists for years. The answer lies in particle collision geometry and energy distribution. When a high-energy cosmic ray collides with an atmospheric particle, the energy is distributed among many particles created in the collision. The energy density at any point never quite reaches the critical value needed to nucleate a true vacuum bubble. It's like trying to boil water by hitting it with a hammer. The hammer might carry enormous energy, but the energy is distributed over space and time in a way that doesn't reach the critical temperature for boiling. However, this realization cuts both ways. If cosmic rays haven't triggered vacuum decay despite billions of years of bombardment, it suggests our vacuum is either more stable than calculations indicate, or the energy threshold for decay is higher than we think. This is evidence, but it's evidence that points in multiple directions, deepening rather than resolving the mystery. The anthropic question. The most remarkable discovery involves something that seems unrelated to particle physics: the existence of intelligent observers like us. In 1983, physicist Brandon Carter formalized what he called the anthropic principle, the observation that any universe we find ourselves in must be compatible with our existence. We cannot observe a universe in which observers cannot exist. Applied to vacuum stability, the anthropic principle suggests something profound. If our universe's vacuum were completely unstable, decaying rapidly after the Big Bang, structure would never form. Galaxies, stars, planets, and life would be impossible. The fact that we exist to ask questions about vacuum stability means we must find ourselves in a universe where the vacuum has survived at least 13.8 billion years. This doesn't mean our vacuum is absolutely stable. It means we're experiencing selection bias. We exist in a universe where the vacuum hasn't decayed yet. There might be countless other universes, other regions of a vast multiverse, where the vacuum decayed quickly, but nobody is there to observe it or wonder about it. In 2016, physicist Sean Carroll and his collaborators at Caltech explored the implications of combining vacuum metastability with eternal inflation, a theory in which universes constantly butt off from one another. They showed that metastability is not only compatible with our existence, but might actually be typical. In an eternally inflating multiverse, universes with metastable vacuums might be common, and observers like us would naturally find themselves in such universes. The evidence extends beyond particle physics into the realm of cosmology, quantum mechanics, and the very nature of existence itself. To truly understand vacuum decay, we need to visualize the energy landscape of the universe. Imagine a vast, multidimensional surface with hills, valleys, and plateaus. Each point on this landscape represents a different configuration of the quantum fields that permeate space. The height at each point represents the energy density of the vacuum in that configuration. Our universe exists at some point on this landscape. The question is, are we at the lowest point, the deepest valley? Or are we on a plateau or in a shallow depression with deeper valleys elsewhere? The work of Coleman, DeLucia, and subsequent physicists showed that the Standard Model predicts a landscape with at least two important features. There's the valley where we currently exist, with an energy density compatible with our observations, and there's a much deeper valley at higher energy scales, the true vacuum. Between them is an energy barrier, a mountain ridge that normally prevents us from falling into the deeper valley. Quantum tunneling allows the universe to occasionally, randomly, tunnel through this barrier, creating a bubble of true vacuum. The probability of this happening at any point in space and time is infinitesimally small. But space is vast and time is long. Over cosmic timescales and across cosmic distances, the improbable becomes inevitable. This forces us to reconsider fundamental assumptions about the permanence of physical law. We usually think of the laws of physics as eternal and unchanging. But if we exist in a false vacuum, the laws we observe are contingent on our vacuum state. Different vacuum states mean different laws. Reality itself is conditional.
Competing interpretations. Not all physicists agree on the interpretation of vacuum metastability. There are several competing frameworks for understanding what the calculations tell us. The conservative interpretation, held by many particle physicists, is that the calculations are correct within the Standard Model, but the Standard Model is incomplete. Beyond the Standard Model, there are additional particles and forces we haven't discovered yet. These new physics could stabilize the vacuum, moving us from metastability to absolute stability. Theories like supersymmetry,
which proposes that every known particle has a heavier supersymmetric partner, could provide this stabilization. String theory, which attempts to unify quantum mechanics and general relativity, also suggests mechanisms that might stabilize the vacuum. The problem is that decades of experimental searches have found no evidence for supersymmetry or string theory. The Large Hadron Collider has been colliding particles at record energies for over a decade, and everything it has found fits perfectly within the Standard Model. No supersymmetric particles, no extra dimensions, no exotic phenomena. This doesn't mean these theories are wrong, but it does mean that if they are correct, their effects occur at energy scales even higher than we can currently probe. A second interpretation comes from cosmologists who take the metastability seriously. Stephen Weinberg, Joe Licken, and others have argued that we should accept the calculations at face value. We live in a metastable universe. The vacuum will eventually decay, but the timescales involved are so enormous that it's not a practical concern. The vacuum might survive another 10 to the power of 100 years or 10 to the power of 600 years. By the time vacuum decay becomes likely, all stars will have burned out, all black holes will have evaporated through Hawking radiation, and the universe will be a cold, dark, empty place. Vacuum decay would destroy a universe that is already dead in any meaningful sense. A third, more radical interpretation involves the multiverse. If eternal inflation is correct, and our universe is just one bubble in an endlessly inflating cosmic foam, then vacuum decay might simply be the mechanism by which new universes are created. When our false vacuum decays, it doesn't destroy everything. It transforms into a new universe with different physical laws. From the perspective of eternal inflation, vacuum decay is not death, but metamorphosis, the birth of new realities from old ones. What leading physicists believe. Joseph Licken, a theoretical physicist at Fermilab who has spent decades studying vacuum stability, summarized the situation in a 2013 lecture. The universe wants to be in a different state, and eventually it will get there. It's just that it could take longer than the current age of the universe by a factor of 10 to the power of 100 or more. So it's not anything to lose sleep over. Frank Wilczek has expressed a different perspective, one tinged with philosophical wonder. In several lectures and articles, Wilczek has pointed out that vacuum metastability suggests our laws of physics are temporary, local, contingent. This raises profound questions. Why these laws? Why this vacuum state? If the laws of physics are contingent, subject to change, then physics itself becomes a kind of cosmic history, the story of how one set of laws evolved from another. Stephen Hawking, before his death in 2018, expressed concern about vacuum decay in a different context. In his final paper, published posthumously, Hawking and his co-author Thomas Hertog discussed eternal inflation and the multiverse. Hawking worried that in an eternally inflating cosmos, most universes would be extremely unstable, with vacuums that decay almost immediately. The existence of long-lived universes like ours would be rare, which raised questions about probability and prediction in cosmology. Max Tegmark, a physicist and cosmologist at MIT, has argued that vacuum metastability might actually be evidence for the multiverse. In his book, Our Mathematical Universe, Tegmark points out that absolute vacuum stability would be surprising. It would require fine-tuned values for the Higgs mass, top quark mass, and other parameters. Metastability, on the other hand, seems more generic. It doesn't require special tuning. In a multiverse where different universes have different parameters, metastability might be common, and we find ourselves in such a universe simply because that's where observers can live long enough to ask questions. But perhaps the most philosophically interesting perspective comes from Sean Carroll, who has written extensively about the arrow of time and entropy. Carroll points out that vacuum decay is intimately connected to the second law of thermodynamics, the law that says entropy always increases. A false vacuum is a low entropy state. The universe is far from equilibrium. Vacuum decay is simply the universe's eventual slide toward higher entropy, toward equilibrium. From this perspective, vacuum decay is not an exotic quantum phenomenon, but an inevitable consequence of thermodynamics. The universe is unwinding, relaxing toward a state of maximum disorder, and vacuum decay is part of that cosmic unwinding. Ongoing research and experiments. Several research programs are actively investigating vacuum stability and its implications. At CERN, physicists are conducting precision measurements of the Higgs boson's properties. The more accurately we know the Higgs mass and its couplings to other particles, the better we can calculate vacuum stability. The High Luminosity Large Hadron Collider, an upgrade scheduled for completion in 2019, will collect 10 times more data than the current LHC, allowing for unprecedented precision in these measurements. In Japan, physicists are planning the International Linear Collider, a proposed particle accelerator that would collide electrons and positrons rather than protons. This machine could measure the Higgs boson's properties with even greater precision than the LHC, potentially resolving whether our vacuum is definitively metastable or might still be absolutely stable within the uncertainties. Beyond particle physics, astronomers are using gravitational wave detectors to search for exotic phenomena that might be related to vacuum structure. The Laser Interferometer Space Antenna, or LISA, is a planned space-based gravitational wave detector scheduled for launch in the 2030s. LISA will be sensitive to gravitational waves with much longer wavelengths than ground-based detectors like LIGO, potentially allowing it to detect gravitational effects from cosmological phase transitions or even, hypothetically, distant vacuum decay events. Technologies that might help. Recent breakthroughs suggest new approaches to understanding vacuum stability. In 2017, physicists at MIT and Harvard developed quantum simulation techniques that allow them to create analogs of vacuum decay in the laboratory. Using ultra-cold atoms trapped in optical lattices, they created systems that mimic quantum field theory in low dimensions. While these systems don't directly simulate the vacuum of our universe, they allow physicists to study phase transitions and tunneling phenomena in controlled settings, testing theoretical predictions about how decay bubbles nucleate and expand. Advances in quantum computing might also shed light on vacuum stability. Calculating vacuum decay rates requires solving complex equations that are beyond the reach of classical computers. Quantum computers, which exploit quantum superposition and entanglement, might be able to perform these calculations more efficiently. Companies like IBM, Google, and startups like Rigetti are developing quantum computers with increasing numbers of qubits, the quantum analog of classical bits. Within the next decade, these machines might be powerful enough to simulate quantum field theory with unprecedented accuracy. There's also hope that future particle accelerators could probe energy scales closer to where vacuum instability emerges. While we can't build accelerators that reach 10 to the 10th GeV with current technology, several groups are researching novel acceleration techniques. Plasma Wakefield accelerators, which use plasma waves to accelerate particles, can achieve acceleration gradients thousands of times stronger than conventional accelerators. In 2014, researchers at SLAC National Accelerator Laboratory used this technique to accelerate electrons to high energies in a device just 1 meter long. Scaling up this technology could potentially allow us to probe higher energy scales in smaller, less expensive facilities.
Predictions and future discoveries. What might we discover in the coming decades? Several possibilities emerge from current research. First, precision measurements of the Higgs boson and top quark might reveal that their masses are slightly different from current measurements, perhaps shifting our universe from metastability to absolute stability, or vice versa. Even a small change in measured values could dramatically affect the stability calculation. Second, we might discover new particles or forces that stabilize the vacuum. Supersymmetric particles, if they exist, would contribute to the effective potential and could shift the vacuum from metastable to stable. Even a single new particle with the right properties could make all the difference. Third, we might find direct evidence of extra dimensions or other features predicted by string theory. If these exist, they would fundamentally alter our understanding of vacuum structure. String theory predicts a vast landscape of possible vacuum states, perhaps 10 to the power of 500 different vacuums, each corresponding to a different universe with different laws of physics. Our metastable vacuum might just be one point in this enormous landscape. Fourth, gravitational wave astronomy might reveal unexpected phenomena. Some theoretical models predict that vacuum decay in the early universe could leave signatures in the gravitational wave background, subtle ripples in space-time that permeate the cosmos. Future detectors might find these signatures, providing direct evidence of vacuum phase transitions in the universe's past. Connection to broader cosmological questions. Vacuum stability connects to nearly every major question in cosmology. The mystery of dark energy, the accelerating expansion of the universe, might be related to vacuum energy. The smallness of the cosmological constant might be telling us something about our position in the vacuum landscape. The mystery of dark matter, the invisible substance that makes up most of the matter in the universe, could also be connected. Some theories propose that dark matter consists of particles associated with additional quantum fields beyond those in the standard model. These fields would have their own vacuum structures, their own energy landscapes. The interplay between the standard model vacuum and dark sector vacuums could affect stability in ways we don't yet understand. And even the Big Bang itself might be understood as a vacuum phase transition. In the earliest moments of the universe, the vacuum might have been in a very different state, perhaps a state with all forces unified. As the universe expanded and cooled, the vacuum underwent phase transitions, separating the forces and setting the parameters we observe today. The universe's entire history could be read as a journey through the vacuum landscape, a series of phase transitions that brought us from the symmetric, unified vacuum of the Big Bang to the broken, asymmetric vacuum we inhabit now. And this raises the ultimate question: what caused the Big Bang? Some cosmologists speculate that our universe itself might have nucleated as a quantum fluctuation, a bubble of false vacuum that tunneled into existence from nothing. If vacuum decay can create bubbles of new universe within our universe, perhaps our entire universe is itself such a bubble, born from the decay of some previous vacuum state. Reality might be an infinite tower of vacuum decays, universes creating universes in an endless cascade. The nature of reality. The most profound implications emerge when we consider what vacuum metastability tells us about the nature of reality itself. We live in a universe of laws, or so we thought. Gravity attracts, light travels at a constant speed, electrons have a specific mass and charge. These seemed like fundamental truths, eternal facts about reality. But vacuum metastability suggests otherwise. These laws are contingent on our vacuum state. Change the vacuum, and you change the laws. The rules we observe are not eternal, but temporary, artifacts of the particular energetic configuration of the quantum fields that fill space. This realization transforms physics from a search for eternal truth into something more like archaeology. We're uncovering the history of our particular cosmic environment, understanding why space has the properties it does right now, in this era, in this phase. The laws of physics become historical accidents, frozen in place by the universe's thermal history, but not fundamentally necessary. Philosopher Hilary Putnam once asked whether mathematics is discovered or invented. Physicists have long debated whether physical laws are discovered or invented. Vacuum metastability suggests a third option. Physical laws are neither discovered nor invented, but evolved. They emerged from initial conditions, shaped by phase transitions and symmetry breaking as the universe cooled from the Big Bang. In another universe, with different initial conditions or different tunneling events, the laws would be different. This raises vertiginous questions about causation and explanation. When we ask why the electron has the mass it does, the answer might ultimately be because our vacuum happened to end up in this particular state. There's no deeper reason. It's contingency all the way down.
The Paradox of Knowledge 105 to 110:00. There's a strange paradox embedded in our knowledge of vacuum decay. The more precisely we measure the Higgs boson, the more confidently we can say whether our vacuum is metastable. But knowing that we're in a metastable vacuum doesn't help us. We can't prevent decay, we can't detect a decay bubble before it reaches us, we can't escape to a safe region of space because there is no safe region. The knowledge is purely theoretical, satisfying our curiosity but not empowering us to act. This is unusual in science. Usually, understanding grants agency. We understand disease, so we develop medicine. We understand climate, so we can predict and prepare for storms. We understand nuclear physics, so we can build reactors or weapons. But understanding vacuum decay grants no agency whatsoever. It's pure knowledge without application, an answer to a question that changes nothing about how we live. Some philosophers argue this makes vacuum decay the ultimate test case for the value of knowledge for its own sake. If we discover tomorrow that our vacuum will certainly decay in 1 million years, how should we respond? Should we despair that our descendants are doomed? Should we take comfort that we have 1 million years, vastly longer than human civilization has existed? Should we intensify our search for a solution, even though no solution seems possible? These questions touch on deep issues in ethics and meaning. If everything is temporary, if even the laws of physics are provisional, what grounds are there for saying anything matters? How do we find meaning in a universe that will eventually erase not just our works, but the very possibility of works like ours existing? Yet perhaps there's a strange comfort in vacuum decay. It guarantees that nothing lasts forever, but it also means we're part of a cosmic story that's still being written. The universe is not static, not settled into its final state. It's dynamic, evolving, moving towards some destination we cannot foresee. We exist during an interesting chapter of cosmic history, an epoch where structure and complexity are possible, where the vacuum hasn't yet relaxed into its true ground state. Unsolved mysteries and remaining paradoxes, 110 to 115:00. For all we've learned about vacuum stability, profound mysteries remain. Why do the Higgs and top quark have the masses they do? These masses seem fine-tuned to produce metastability rather than absolute stability or rapid decay. Is this a coincidence, a selection effect? Evidence of some deeper principle we don't understand? Why is the cosmological constant so small? If we're in a false vacuum, shouldn't the vacuum energy be much larger? The discrepancy between theoretical predictions and observed values remains one of the greatest unsolved problems in physics. What happened in the first moments of the Big Bang? Cosmologists believe the early universe underwent a period of rapid expansion called inflation, driven by vacuum energy. But which vacuum? Was inflation itself a phase transition from some even earlier vacuum state? And if so, what triggered the transition? Are there other vacuum states beyond the false vacuum and true vacuum predicted by the standard model? The equations suggest a landscape with many local minima, many possible vacuum states. Each would have different laws of physics. Could the universe exist in multiple vacuum states simultaneously, with different regions having different laws? Could there be domain walls, boundaries between regions with different vacuums somewhere in the cosmos beyond our horizon? Could we ever predict when or where vacuum decay will occur? The probabilistic nature of quantum tunneling means the answer is almost certainly no. The decay is fundamentally random, uncaused in any deterministic sense. But some physicists have speculated about whether extreme astrophysical events, like colliding black holes or merging neutron stars, might slightly increase the local probability of decay. If so, these events might serve as cosmic warning signals, though the warning would come far too late to matter. Multiple possible futures, 115 to 120:00. The evidence suggests several possible futures for our universe depending on which interpretation of vacuum stability is correct. Future 1. We discover new physics that stabilizes the vacuum. Supersymmetry or some other beyond standard model theory proves correct. The vacuum is actually absolutely stable after all, and we can rest assured that the laws of physics are truly eternal. This would be the conservative outcome, confirming that our universe is built to last. Future 2. We confirm metastability, but find the decay timescale is truly cosmic, 10 to the power of 500 years or more. The vacuum will eventually decay, but so far in the future that it's irrelevant. By the time decay becomes likely, the universe has already ended in any meaningful sense. This is the so what scenario, where metastability is real but doesn't matter. Future 3. We discover the decay timescale is shorter than expected, perhaps only 10 to the power of 100 years. This is still enormously long, but it means vacuum decay could occur during an era when the universe still contains structure, perhaps even life. This would reframe vacuum decay as a genuine cosmological concern, something that future civilizations billions of years from now might need to contemplate. Future 4. Vacuum decay has already occurred elsewhere in the universe, beyond our cosmic horizon. Right now, decay bubbles are expanding through distant regions of space, destroying galaxies we will never see, transforming vacuum states in parts of the universe we can never observe. From our perspective, this is indistinguishable from Future 2, but cosmologically, it means the universe is heterogeneous, a patchwork of different vacuum states. Future 5. The multiverse interpretation is correct. Our universe is one bubble among countless others in an eternally inflating cosmos. Vacuum decay is happening constantly, creating new universes with new laws. Our false vacuum will eventually decay, but this isn't an ending. It's a transition, the birth of new realities from the death of our own. Consciousness, life, and complexity might arise again in the daughter universes, continuing the cosmic story in forms we cannot imagine. Which future is real? We don't know yet. We may never know, but the search continues.
The journey we've taken. We began with a simple question: is the vacuum of space stable? We've journeyed through Sidney Coleman's equations in the 1970s, through the discovery of the Higgs boson in 2012, through calculations of effective potentials and quantum tunneling rates. We've seen how the masses of fundamental particles determine the stability of reality itself, how black holes might catalyze decay, how cosmic rays provide evidence of our vacuum's resilience. We've explored competing interpretations of what metastability means. Is it a sign that we don't fully understand physics? Is it a practical irrelevance because the timescales are so vast? Is it evidence of the multiverse? We've heard from leading physicists: Licken's reassurance, Wilczek's wonder, Hawking's concern, Carroll's thermodynamic perspective. We've looked toward the future: new colliders, quantum computers, gravitational wave detectors, technologies that might help us probe deeper into the nature of the vacuum. We've connected vacuum stability to dark energy, dark matter, the Big Bang itself, showing how this one question touches every aspect of cosmology. And we've confronted the ultimate implications: that physical laws might be temporary, that reality is contingent, that everything we know could transform in an instant if a quantum fluctuation occurs in just the right way. What we've learned. The current scientific consensus is clear. Based on the standard model of particle physics and the measured masses of the Higgs boson and top quark, our vacuum is almost certainly metastable. We live in a false vacuum that will eventually decay to a true vacuum of lower energy. The timescale for this decay is extraordinarily long, perhaps longer than 10 to the power of 500 years, far exceeding the current age of the universe by an incomprehensible factor. But consensus doesn't mean certainty. The calculations depend on the standard model being the complete description of particle physics, which it almost certainly is not. New physics at higher energies could change everything. Moreover, the vacuum decay rate is sensitive to parameters we can't measure directly, like the precise shape of the effective potential at energy scales far beyond experimental reach. What we've learned with confidence is that the universe is stranger than we imagined. The vacuum is not passive emptiness, but a dynamic entity with structure and energy. The laws of physics are not eternal Platonic ideals, but emerge from the properties of this vacuum. Change the vacuum, change the laws. Reality is more fluid, more contingent than our everyday experience suggests. We've also learned humility. For all our sophisticated mathematics and powerful experiments, we cannot predict when or where vacuum decay will occur.
We cannot prevent it or escape it. We are passengers on a cosmic journey whose destination is obscured by quantum uncertainty and the vast scales of space and time. What remains unknown? The greatest mysteries endure. We don't know why the Higgs boson has the mass it does. We don't know why the cosmological constant is so small. We don't know what happened in the first fraction of a second after the Big Bang. We don't know whether we're alone in the cosmos, or whether other vacuums, other universes with different laws, exist beyond our horizon. We don't know whether vacuum decay is truly random, or whether some deeper principle governs when and where it occurs. We don't know what happens inside a true vacuum bubble. Do new forms of matter and energy emerge? Could structure and complexity arise even with different laws of physics? Could life, perhaps unrecognizable to us, exist in the true vacuum? We don't know our ultimate fate. Will our descendants, if they exist billions of years from now, witness the vacuum decay? Will they have technologies we can't imagine, ways to detect approaching bubbles, or even influence vacuum stability? Or will we and they simply cease to exist one day when a bubble wall passes through us at the speed of light? These unknowns are not failures of science, but frontiers, invitations to future discovery. Every answer we found has revealed new questions, deeper mysteries. This is how science works. This is how understanding grows. The human quest for understanding. In 1973, Sidney Coleman sat at his desk at Harvard, working through equations that described empty space. He wasn't thinking about existential threats or cosmic doom. He was simply following the mathematics wherever it led, trying to understand the quantum nature of the vacuum. What he found was unsettling, but he published it anyway because truth, even uncomfortable truth, is the goal of science. 50 years later, we have more data, better calculations, deeper understanding. But Coleman's core insight remains. The vacuum might be unstable. This knowledge doesn't help us survive. It doesn't improve our lives. It doesn't solve practical problems. Yet we pursue it anyway, because we're human, because we wonder, because we need to know. The story of vacuum decay is ultimately a story about curiosity, about our species' relentless drive to understand the universe, even when that understanding is terrifying. We look into the abyss and take notes. We measure our own impermanence with precision. We calculate the probability of our erasure. And having done so, we continue living, working, loving, creating, as if nothing has changed. Perhaps nothing has changed. We've always known we're temporary. Vacuum decay simply extends our temporariness to the cosmos itself. The universe that gave birth to us will someday transform into something else, something where we cannot exist. But that someday is so distant that it might as well be never. Or perhaps everything has changed. Knowing that even physical laws are temporary, we might find new appreciation for the laws we have, for the cosmic accident that allows atoms to bind, stars to shine, life to emerge. We're the universe contemplating itself during a brief window when such contemplation is possible. That's not tragic, that's miraculous. The universe is vast. The mysteries are endless. The journey continues. And for now, in this moment, the vacuum holds. Reality endures. We remain.